Okay, so somebody sent like 7 questions on mathematical induction. So we are going to prove it together, and I hope you also find this interesting. So the question number 1 says that we should show that 1 plus 3 plus 5 plus dot dot up to 2n minus 1 is equal to n squared. So let's do this together. Now, first of all, I want us to know that 1 plus 3 plus 5 plus 1 dot 2n minus 1 equal to x squared is showing us the sum of all the terms for any value of n. So we are required to prove this by mathematical induction. Now, when you're asked to prove anything by mathematical induction, know that there are 3 conditions that must be met, right? So, first of all, since this is showing us sum of our own sequence, let us denote it as Sn is equal to 1 plus 3 plus 5 plus the dot. And remember, this expression here is telling you the rule guiding this. So this is for n10, that is the undefined, equal to n squared. But remember, Sn is just equal to n. If we use this expression, you get all of this. So what is the first condition that you must prove under inductive mathematical induction? First condition is the base case. Prove that the base case holds, and for a base case you denote that your n should be equal to 1. So that is where you see n, you write 1. So our definition Sn equal to n squared means substitute 1 where you see n. So this becomes x1 is equal to n squared. But I want you to understand this. Sn means the sum of the first term. Now go back to the series that we're given. The first term here is 1. This is the sum. So writing 1 here is equal to 1 squared is 1. So you can see that by substituting the value of n into our series, we actually got the first term, which is 1, and here it is. So let me explain further, though it is not necessary, but just to confirm that you are on the right track. Let's try it. Now let's take it that n is equal to 2, that is n is the second term. So this is going to be s2 is equal to, this is our formula, right? So x2 is going to be equal to 2 to the power of 2. Remember, 2 here for n and then the square. Now go back to the question. Sum of the first 2 terms means the first 2 terms, and we have 1 plus 3. So we have 1 plus 3 is equal to 2 square is what? 4. Now add the left hand side. 1 plus 3 will give you 4 equal to 4. So it shows that this is actually the rule with which if you substitute any value of n, you get the complete series here. So having confirmed that at n equal to 1, the rule holds. At n equal to 2, the rule holds. You can actually continue testing it up to 3. So s3 is going to be 3 to the power of 2, and x3 means the sum of the first 3 terms. So this is 1 plus 3 plus 5. And okay, 3 squared gives us what? 9. Add this place. 1 plus 3, 4. 4 plus this, 9 is equal to 9. So it will agree with me that any value you choose for n, it will hold in that expression. So this, from here to here, we are just proving to know that it is correct. So let's go on with the second condition. I told you that to prove by mathematical induction, it requires that 3 conditions must hold. Now, having proven that If n is 2, this is true. If n is 3, this is true. It can be n equal to 3, n equal to 4, n equal to 1000. So since we don't know the definite term for n, we are going to assume the hypothesis case. And this is the hypothesis case. Here we are assuming. So we assume that under the hypothesis case, remember the first case was the base case, the second case is the hypothesis case. Here we are just making conclusions based on assumption. We assume that anytime that for any arbitrary number k, I said if you put any value of n, it will hold. So since we don't know the definite term, let n be k. So sk is now going to be what? K square. But remember, the full definition of sk is 1. Oh, this place is screwed up. So for sk, any place you see n, you are going to replace it with k. So we have 1 plus 3 plus 5 plus dot 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 plus. So you can see n here, so replace it with what? K minus 1 equal to, there's an n square there, that is k square. So this is our hypothesis case. In this case, we can't prove further than this, but just to assume that if this is the case, then we'll still get the same value. Now, what is the last and third condition? The third condition, that is condition 3, is our inductive case. For inductive case, we are saying that if n equal to k gave us this, then let us get the next term after k. Therefore, let n be equal to k plus 1. And for k plus 1, go back to your sk and increase the next term. So this is going to be 1 plus 3 plus 5 plus 1 dot dot plus. Remember, this was the value for the first k, right? Now we are increasing additional k anywhere you see k. So in the formula we had 2n, so we are going to have 2, remove that place, I don't like writing this place of n, and write k plus 1 minus 1 that is outside equal to, on the left hand side we have n squared, so this is going to be k plus 1 all squared. Now this is actually the fun part of mathematical induction. The other ones were just direct, and that's it. Now if you compare this part here to what we have here, you see that they are the same, right? So from our hypothesis case, we said that this expression should be summarized as equal to k squared. So instead of writing these terms back, it means this thing is equal to k squared. So we are going to replace it with k squared plus, so bringing this one, we are going to have 2 into k plus 1 minus 1, right? And on the right hand side, k squared means k plus 1 times another k plus 1. Square means multiply that thing 2 times. So let's open this bracket. We are going to have k squared, and remember the m under inductive case, the left hand side must give us the right hand side. I'm going to explain in other examples different ways we're going to do. For this is direct substitution, so it's very easy to do. So 2 times k will give us 2k, 2 times 1 will give us 2 minus the 1 outside equal to, here we have n into open one bracket against the other bracket. So we have on our left hand side k squared plus 2k, so plus 2 minus 1 will give us plus 1, right? Equal to this side, k times k will give us k squared, k times 1 will give us plus k, plus 1 times k will give us k, plus 1 times 1 will still give us 1. So bringing this, k squared plus 2k plus 1 is going to be equal to k squared. K plus k will give us 2k plus 1. Now, let's take a look at the left hand side. Compare it with the right hand side. Are the terms the same? We have k squared, 2k, 2k, 1 and 1. So this shows that when n is equal to k plus 1, sk plus 1 is going to be k squared plus 2k plus 1. And this also proves that if the value of k is known and you substitute, you get the exact number that will be at this point. Now, having achieved the first condition, which is the base case, will prove that the left hand side is equal to the right hand side. The hypothesis case gave us an assumption that for n equal to k, this is what we are going to have. And the beauty of this hypothesis level, it helps in imputing its equivalence when solving in the inductive case. Now, for this very question, we have proven that all the three conditions hold for the sum of series. That's the series given here. So it therefore shows that by mathematical induction as required, we have proven that this statement defined by this expression is true for any value of n. Stay connected. I'll be dropping the second question. Altogether, the questions are 7, and each question has a different approach in solving. So please comment and kindly share your view if there is any other way to do it. Thank you.